Welcome back, guys. Continuing of Laplace domain for transient solutions. Here in this lecture, we'll continue how the Laplace applicable for standard formulas and all. So you have the Laplace of uh, this is a sine omega t. Sine omega t. So the Laplace of sine omega t is so omega by s square plus omega square. Okay. So for time concerned, I'll solve how the Laplace of sine is came. So you have Laplace of sine t. Take say omega t. So this you can be written as omega sine omega t as L into e power j omega t minus e power minus j omega t by 2j. So this is the known complex form of omega sine omega t. So we'll divide this, separate the equations, separate this. So you'll get Laplace of e power j omega t by 2j minus of Laplace of e power j omega t by 2j. So you bring that numerator outside, denominator outside, 2j. So Laplace of e power j omega t and minus of Laplace of 2j e power minus j omega t. So 1 by 2j of Laplace of j omega t means Laplace of at equal to what? 1 by s minus a. Similarly, Laplace of e power minus j omega t is 1 by s minus j omega minus of 1 by Laplace of e power minus j omega t is s plus j omega. So you solve this content, these things, and you will be getting a value of omega by s square plus omega square. So in the transients, you no need to do all these things. Only you need to remember the Laplace of sine omega t equal to omega by s square plus omega square. So you will be getting a either our concern is to find change in inductor value, current change in inductor value, and current change in inductor value and voltage across capacitor. So the response of I of t and V of t for any RLC circuit. So for any combination of RLC circuit, so the response may be in the form of this form. So in that you will to apply inverse Laplace domain. So inverse of this is, so Laplace of inverse Laplace inverse of omega by s square plus omega square is sine omega t. So you will in your mind you need to understand, if Laplace of sine omega t is omega by s square plus omega square. So why you need to remember this equation is, in your response of I of t and V of t, you will be getting a value of this form. So inverse of this is sine omega t. So for that reason you need to remember few Laplace transforms. Similarly, Laplace of cos omega t equal to s by s square plus omega square, and then Laplace of e power minus at sine omega t. So by this you'll get omega by, in s place you need to apply s plus a whole square plus omega square. This is we already seen before class by complex translation formula, based on complex translation formula. So that is Laplace of e power minus at f of t is f of s plus a form. So this is the formula of Laplace of e power minus at sin omega t equal to omega by s plus, in place of s you need to place s plus a. So similarly Laplace of e power minus at cos omega t. So Laplace of this thing is s plus a by s plus a whole square plus omega square. So similarly Laplace of t e power minus at. So Laplace of t is what? 1 by Laplace of t equal to 1 by s square. So in place of s you need to place s plus a, that is 1 by s plus a whole square. So these are the few Laplace domain formulas you need to understand. So in quickly we'll move to some other concepts. So few standard Laplace domains, Laplace equations, and later we'll solve a few inverse Laplace of few forms. So Laplace transform of so in this section some standard Laplace transforms. So Laplace, you already know these things. Laplace transforms. So see, this is f of t, the function f of t, and the Laplace of t. So Laplace of constant k is k by s, and Laplace of function t is 1 by s square. So if you have a constant k into t is t, then it is k by s square. Similarly Laplace of t power n, then that is n factorial by s power n plus 1. Similarly Laplace of e power minus at. So e power exponential of Laplace e power minus at is 1 by s plus a. Again e power at is 1 by s minus a. The Laplace of e power minus at t power n. So Laplace of t power n is n factorial by s power n plus 1 factorial. In place of s you need to place s plus a. So Laplace of e power n by is n factorial by, in place of s you need to place s plus a. S plus a whole square n whole power n plus 1. Similarly now you saw Laplace of sin omega t. So Laplace of sin omega t means omega by s square plus omega square. Laplace of cos omega t is s by s square plus omega square. So Laplace of similarly e power minus at sin omega t is omega by s plus a whole square plus omega square. Again Laplace of at minus cos omega t is s plus a by s plus a whole square plus omega square. Okay. So now we'll solve one. We'll go to directly. So this is the Laplace of this Laplace transform of few functions. So now we'll solve some inverse Laplace transforms. So what is inverse Laplace? Before going to solve that inverse Laplace, I would like to give a constant like the standard Laplace transforms. So we generally use this terminology, some standard Laplace transforms. So standard Laplace transforms, you have standard signals. So you know already Laplace transform of constant k. So what is this k? And Laplace transform of t. So what is this t? And Laplace transform of 1. Okay. So in for generalizing any signal for any system, we need input signal. So for constant input signal, what is the response of the system, you need to understand. If you give a step function, so it's the standard signals are you have a step function, a ramp function, and impulse function. Okay, these are the standard signals used, and we have a few more parabolic function, etc. Now we'll see what is step function. So step function is represented by u of t. So the u of t equal to 1 for t greater than equal to 0, then it is 0 for t less than 0. So we'll discuss what is step function here. So the representation of this step function is it is at t greater than 0. So at t greater than 0, it is the constant having value 1. So u of t is 1. That means the magnitude of this function at t greater than 0 is 1. That is in circuits you solved that circuit, any circuit. So the sample circuit, you place the switch and you given this source. So the source are maybe 10 volts. So at t equal to 0, you switch on the circuit. That means your t equal to 0, if this is magnitude 1, so you switch on the circuit, then that means you are giving one constant voltage DC. This is DC. So representation of DC, so in Laplace, you will form in the step function. So you have many sources. I already said you have sinusoidal waves, you have constant supply, that is DC, and you have alternating current source, AC sources, and all. So what is alternating sources means it is having symmetrical, then it is alternating. So it have two positive cycle and negative cycle. This is sin omega t. Okay, so for time being, for the constant so DC, we'll rely on step function. So representation of this this signal, say for example this circuit I kept, this is 1 volt. So, okay, the same circuit can be represented like this. So this function is, if I keep u of t, that means for t less than 0, the switch is open, so this is inactive. That means at t less than 0, it is having 0 magnitude. At t greater than 0, the source is acting in this circuit. Okay, so in new circuits they may ask you give this form. So in circuits if they won't give any switch and all, just they will give one source u of t. If they ask u of t means at t greater than 0, the magnitude with some magnitude, some 10 u of t I gave the signal input source. That means this input source is acting with 10 magnitude, you need to understand. Okay, now in place of 10 u of t, I kept like this 10 minus u of t. If I keep minus u of t means the step is active for t less than 0. This is this form. Up to 2 less than 0, the source is acting. That means t less than 0 means switch is opened. In this case 10. For switch open directly, you need to represent means 10 u of minus t. For switch closing means 10 magnitude of u of t. Okay, this is the normal representation of step function. So we have another function, ramp function. So ramp function. So ramp function is generally represented by r of t. So ramp r of t. So r of t equal to what? It is a function t for t greater than 0, and that is equal to 0 for t less than 0. With varying of time, the magnitude is also varying with slope 1 is called a ramp function. Okay, so this one kind of input source for this signal. So ramp t of, if you give a ramp signal t, the circuit will be acting in different form. And we have a impulse function delta of t equal to 1 for t equal to 0, and it is 0 for t less than 0. That is, this signal is represented like this. The ramp signal at t equal to 0 only, it is having magnitude 1. At any point of time, it is 0. Then signal is called impulse signal. That's one impulse, just one impulse only. So digital impulse, will say digital input. This is kind of one impulse only. So we have the combination of this ramp, step, impulse signals. So the relation between, so we have the concept called relation between standard functions. So relation between standard function means, so if you derive differentiation of ramp signal, so if you differentiate this ramp signal, you will be getting a step signal. So differentiation of this ramp signal, so at each piece of time, if you differentiate this signal, you will be getting a step signal. Again, integral of, similarly opposite of this, integral of u of t is, so if you both integrate both sides, integral of u of t is ramp signal. Similarly, differentiation of u of t, so differentiation of the constant is u of t. Differentiation of u of t is you will be getting a impulse. Similarly, integration of impulse, you will getting a step. So these are the relations you need to remember. So differentiation of ramp is a step, and integration of step is a ramp, and the differentiation of step is impulse, and integration of impulse is step. Okay. So based on the standard signals, the main Laplace transform you need to remember are so Laplace of, so all the Laplace transforms based on standard signals only. So based on standard signal, Laplace of standard signal. Before you saw the Laplace of functions only. So functions terminating into a standard form, sir, we'll discuss now. So this is not a new topic. Now I'm discussing some standard functions, naming only the difference. The function u of t, and this is the Laplace transform. So first step is unit step function, that is u of t. So Laplace of u of t is 1 by s. A Laplace, that is 1, if Laplace of constant 1 is 1 by s, similarly u of t is 1. So if you're having magnitude a u of t, then Laplace is a by s. Similarly, delayed unit step function. So u of t minus t, you will be represented. Delayed t minus t means instead of switching at t equal to 0, it is switched at t equal to 2. That function u of t function is represented by u of t minus tau. This is represented u of t minus 2. If time t means it will be represented u of t minus t. The Laplace of that function is e power minus ts by s. Okay, e power minus ts by s. Similarly, if this have a magnitude u of t minus this, then it is a of e power minus ts by s. Another will go to unit ramp function. So ramp function r of t, then so ramp function r of t, it is represented as a function t, r of t equal to t. So Laplace of this t is we have 1 by s square. So if this having a magnitude then a of t, then the Laplace of this is a by s square. Similarly, the delayed function, delayed unit ramp input, r of t minus t, then it is having a signal e power minus ts by s square. So e power minus ts only come. So same e power delayed function e power minus ts, e power minus ts square. So again, if this having a magnitude of a t minus t, then the Laplace transform is a of e power minus ts by s square. So e power r of t minus t is Laplace transform is e power minus ts by s square. This is having magnitude a is a into e power minus ts by s square.